Welcome back, chemistry students. We are moving on to section 3, and this is all about the ideal gas law. And I love this little comic. Do you have any history of mental illness in your family? My uncle used the ideal gas law on a liquid. It's only used for gases. 4 interrelated quantities can be used to describe a gas. This is a review from the last couple sections: pressure, volume, temperature, and the amount of gas in moles. This can be made into a mathematical equation by introducing a proportionality constant, now labeled R. This constant, called the gas constant, is a universal constant, a number that's used to interrelate the properties of any gas. Here is our ideal gas law equation, PV equals nRT. It describes the behavior of a so-called ideal gas. But here's the funny thing. There is no such thing as an ideal gas. But real gases at pressures around 1 atmosphere and room temperature usually behave close enough to the ideal that we can use PV equals nRT and it will adequately describe the behavior. Now R, this constant, is calculated under conditions of standard temperature and pressure. You'll see this written as STP, standard temperature and pressure, and at the standard molar volume. Now at standard temperature and pressure, we're at 0 degrees Celsius, or 273.15 Kelvin, a pressure of 1 atmosphere, and the standard molar volume of something tells us that 1 mole of any gas occupies 22.414 liters of that volume. So to find R, using this equation, to get R by itself, I would divide both sides by NT. So PV divided by NT. Let's look at that down here. Pressure of 1 atmosphere, a volume of that 22.414. N means 1 mole of something, and a temperature at the room temperature 0 degrees, 273.15. And we get this constant, 0.082057. Notice the units. This is going to also be key. This constant has a unit of liters atmospheres over Kelvin mole. That means when we're using this equation, our pressure needs to be in atmospheres, the volume needs to be in liters, our temperature, as always, needs to be in Kelvin, and our N is our moles. Here's just a little reminder for our rules when we're doing ideal gas laws. Make sure your temperature is in Kelvin. Make sure if you're given grams that you convert to moles, because N is moles. And make sure that because R's unit is liters, atmospheres, moles, Kelvin, that if you're given a pressure in, let's say, millimeters of mercury, you convert it to atmospheres. If you're given a volume of milliliters, you get it to liters. Let's look at an example here. The nitrogen gas in an automobile airbag with a volume of 65 liters exerts a pressure of 829 millimeters of mercury at 25 degrees Celsius. What amount of gas in moles is in the airbag? So we are given a volume, we're given a pressure, we're given a temperature. Notice that this is different from our other problems because in our other problems we were given an initial pressure and then a pressure that it changed to, or an initial volume and then a volume that it changed to. Here I'm just given one of each, and it's telling me that I want to find N. I've got pressure, temperature, N, and V. We can use the ideal gas law because we also know R. PV equals nRT. Looking at my work, I wrote down my pressure. Notice it's in millimeters of mercury. I gotta convert it to atmospheres. My volume is good in liters. We need to find N. So I took my PV equals nRT and I rearranged it to solve for N. So I divided both sides by RT. N is equal to PV divided by RT. Let's plug in our pressure, our volume, our R, and our T. And we should get, with 2 significant figures, because our volume is 2.9 moles. Why don't you try this one? Write down what you're given and see if you can find the volume of the balloon using our ideal gas law. Let's see how you did. Our pressure, we were given in millimeters of mercury. We needed to convert it to atmospheres. It asked us to find the volume, so I put V question mark. Our N, we were given 1,300 moles. We always know R. And we were given temperature. Make sure you convert it to Kelvin. Using PV equals nRT to solve for V, I divided both sides by that P to get V by itself. nRT divided by pressure. There's my N, there's my R, there's my T, all divided by the pressure that I found. And I was limited by 2 significant figures thanks to my moles, so 3.2 times 10 to the 4th liters, or 32,000 liters. This one might stump you a little bit. Calculate the volume occupied by 43.7 grams of hydrogen at STP. You might look at this and say, I'm only given one variable. I'm given mass. Mass is nowhere to be found in PV equals nRT. But I'm told that it's hydrogen, so I can go from grams to moles because I can find the molar mass of hydrogen. And we are told that this is at standard temperature and pressure. So knowing all of that, I know that hydrogen is 2 H's, so 1.01 times 2, molar mass of hydrogen is 2.02. So I found the moles of hydrogen, which is my N value. I know that standard temperature is 0 degrees Celsius, or 273.15 Kelvin, but we went to the whole number here. And I know that standard pressure is 1 atmosphere. We always know R. The only thing we don't know is the volume. PV equals nRT. To get volume by itself, we got rid of the P, so nRT divided by P. And we should get, since I started with 3 significant figures, 485 liters. Moving on to gas density. The density of a gas at a given temperature and pressure is a useful quantity. Because the amount, or our N, our moles, of a compound is given by its mass divided by molar mass, we can substitute, because we know if I took the grams of hydrogen and divided it by the molar mass, which is grams per mole, those grams cancel and I'm left with moles. So N, our moles, is equal to mass divided by molar mass. So all we did was substitute in for PV equals nRT. We substituted mass over molar mass for that N. Then we can find density. We know density is mass divided by volume, but nowhere in PV equals nRT was there mass before we substituted in mass over molar mass for that N. Now we can rearrange this equation to solve for density, which is mass divided by volume. All I need to do is to get M and V on the same side. I have to multiply capital M on both sides to get rid of that M. Now to get M over V, I need to divide both sides by V so that I have M over V, but that leaves me with MP is equal to M over V RT. But I want MV by itself to solve for density. Density is mass divided by volume. So let's get rid of RT. That gets rid of that. So now I'm left with MV, which is density, is equal to MP or PM divided by RT. This is going to help us. The density of a gas is going to be in units of grams divided by liters. Mass is grams. Our volume, using our ideal gas law equation, volume is always in liters, so grams per liter. Let's do a sample problem together. What is the density of oxygen gas at STP? This equation that we just found is useful because gas density can be calculated from the molar mass, or the molar mass can be found from a measurement of density. We just said that density was equal to mass divided by volume, which is equal to P times M over R divided by T. We know in this equation, oxygen gas, 2 oxygens, so 16 plus 16 has a molar mass of 32. That's going to be my capital M. So we're given M. We are given standard pressure, which is 1 atmosphere. We're given the temperature it's at, which is 0 degrees Celsius, or 273.15. And so therefore I can do my pressure, which is 1, times my molar mass, which is 32, divided by RT, that's my R, that's my T. So my density is then 1.428 grams per liter. See if you can set this one up. Calculate the density of carbon dioxide at STP. Well, I found the molar mass of CO2. I took carbon's mass plus 2 oxygen's mass, and I got 44 grams per mole. I plugged it into our equation. Density is equal to P times M. We were told STP, standard temperature and pressure. Standard pressure is 1 atmosphere times our M divided by our R and our temperature, 273. And I got 1.96 grams per liter. Now here's a little fun fact. Because carbon dioxide from fire extinguishers is denser than air, it settles on top of a fire and it smothers it. When carbon dioxide gas is released from the tank, it expands and it cools significantly, and that white cloud is condensed moisture from the air. When a new compound is isolated in the laboratory, one of the first things we do is determine its molar mass. If the compound is easily volatilized, a classical method of determining the molar mass is to measure the pressure and volume exerted by a given mass of the gas at a given temperature. Let's look at this problem. You're trying to determine by experiment the formula of a gaseous compound you made to replace chlorofluorocarbons in air conditioners. You have determined the empirical formula is CHF2, but to determine the molecular formula, you need to know the molar mass. We can find the empirical mass, but remember, to find that molar mass, we need to know how many times this is multiplied. Is it by 2? Is it by 3? Is it by 4? So you find that a 0.100 gram sample, here's a mass, of the compound exerts a pressure of 70.5 millimeters of mercury in a 256 milliliter container, that's a volume, at 22.3 degrees Celsius, that's a temperature. What is the molar mass of the compound, and what is its molecular formula? First, we've got some unit conversions to do. We were given our mass, yes. We were given a pressure in millimeters of mercury. I put it into atmospheres. We were given a volume in milliliters. I converted it to liters. Temperature in Celsius, I turned it to Kelvin. I'm going to show you 2 different ways to do this. Using that density equation, mass divided by volume is equal to P times M divided by R times T. I did M divided by V is equal to P times M divided by R times T. My only unknown is that molar mass. So I cross-multiplied, I got M by itself, and I got 102 grams per mole for the molar mass of that compound. Now think way back a few chapters ago, where if I knew the empirical formula, that means I could find the empirical formula's mass. So if I take that molar mass and divide it by the empirical mass, in this case I got 2. So I'm going to multiply everything in that empirical formula by 2 to get that molecular formula. But maybe you wanted to go a different route. Maybe you wanted to plug everything right into PV equals nRT because you were given pressure and volume and you know R and you were given T. So the only unknown here is our N. So you could solve for N. We would get 9.794 times 10 to the negative 4th moles. Then I could take my moles and I could take my mass from up here. If I did grams divided by moles, that would give me grams per mole. And that would be my molar mass. And then I would go to this stage and do my molar mass divided by the empirical mass, get 2 and times everything by 2. So there's 2 different ways you could have done this problem. Here's our last problem of this section. Pause the video here, see if you can find the molar mass. Let's see how you did. We were given a mass, we were given a pressure, I converted it to atmospheres. We were given a volume, I got it to liters. We were given a temperature, I got it to Kelvin. Using our density, or M over V is equal to PM divided by RT, I made it a linear equation right off the bat. So I got MRT is equal to VPM. I don't like fractions. So then to find the molar mass, which is capital M, to get it by itself, I divided both sides by VP. So M, the molar mass, is equal to mass times the R times the temperature divided by VP. And I got 27.7 grams per mole.